Conformational isomerism. In the case of alkanes, conformational isomerism is possible because they contain CC single bonds. The CC single bonds of alkanes are easy to rotate. That means they are free of rotation. Due to this free rotation, different spatial arrangement of atoms in the space are possible, and these isomers are, due to this different isomers are obtained. These isomers are called as the conformers or conformations. Okay, conformations or conformers. These are also called as rotamers because these are obtained due to the rotation of the sigma bond. Okay, different spatial arrangement of atoms in the space. Arrangement of atoms in the space. Okay, due to the free rotation of CC sigma bonds. CC sigma bonds. And also we can see that there are infinite number of rotations are possible, and as a result infinite number of conformations are also obtained. Okay, infinite number of conformations. But when these bonds come closer, we can see that there is a weak repulsive force. This weak repulsive force hindered the free rotation. These weak repulsive forces are called as the torsional strain. Weak repulsive force. This is called as torsional strain. Torsional strain is due to bond pair repulsion. Strain is due to bond pair repulsion. And the angle of rotation, while rotation there will be an angle between this rotation, this hydrogen bond, these bonds, these are called as the torsional angle. Torsional angle. It is due to the rotation of CC bond. Due to the rotation of CC bond. Okay. This angle is called as the torsional angle or dihedral angle. Stability of the compound depends upon this torsional strain. As the torsional strain increases, the stability of the compound decreases. Okay, this torsional strain also depends upon torsional angle. Let us discuss with an example. Okay, conformation of ethane. In case of ethane. Conformation of ethane. So ethane contains a CC single bond and each carbon atom contains 3 hydrogen atoms. Okay. So this ethane contains 2 CH3 groups. Okay. 2 CH3 groups. These are rotating. Okay, this CC bond is rotating, and in this case also we can see that there are infinite number of rotations. So infinite number of conformers are possible. Conformations. Let us take 2 extreme conformations. First one is first conformation. First case in which the 2 hydrogen atoms of 2 carbon atoms, okay, because there are two CH3 groups, and in the case of each carbon atom there are hydrogen. So two hydrogen atom of the two carbon atoms are come closer or are closed together. If they are closed together, such conformations are called as eclipsed conformation. Okay. And also we can see that in the case of eclipsed conformation, two hydrogen atoms are very close to each other. So there will be high torsional strain and the stability of the compound will be minimum, or this eclipsed conformation is least stable. This is one extreme case. Next, second case is if the two hydrogen atoms of the two carbon atoms, okay, of CC bond, okay, of each carbon atom are far apart. If they are far apart, such conformations are called as staggered conformation. And we can see that since in this conformation these hydrogen atoms are far apart, so the repulsive force will be minimum or torsional strain will be minimum and it will be most stable. Okay, these are the two extreme cases. And there is an intermediate state between these two, that is called as the skew conformation. Okay. Now we can represent these conformations in two ways. First one is SAWHORSE projection and second one is NEWMAN projection. Let us discuss that. SAWHORSE projection. Okay, and second case is NEWMAN projection. Let us draw the ethane molecule. Okay, it contains one CC bond. This can be represented. CC bond is represented like this, a tilt line. Okay, and there are hydrogen atoms in each carbon atom. This is near to the observer, this is away from the observer. So you can see that hydrogen atoms are very close. Okay, this can be drawn like this. This is the eclipsed form. Eclipsed. In the case of eclipsed, the hydrogen atoms are very close and this carbon is the nearer to the observer. This is away from the observer. Okay, this is the least stable conformation. And now let us draw the NEWMAN projection. This is one carbon and this circle denotes the other carbon. This is the point of intersection. This carbon. Okay. The point of intersection of three hydrogen atoms. Okay, this is the front carbon. Okay, and this is the rear carbon. Hydrogen atoms are attached, and in the case of eclipsed form, we can see that these hydrogen atoms are very close. So we can draw like this. This is the eclipsed form, NEWMAN eclipsed form. Now let us take the staggered form. Staggered. Okay. Draw a tilt structure. Now, in this case, hydrogen atoms are far apart. Okay. This is three-dimensional structure. We can draw like this. Okay. This is the staggered form of SAWHORSE projection. And now, how can we draw this? Since the hydrogen atoms are far apart, we can draw like this. Okay. And this angle is called as the torsional angle. In the case of staggered, we can see that torsional angle is maximum. So, torsional angle maximum means torsional strain will be minimum and the compound will be highly stable. Okay. Now, let us discuss the difference between these two. One is most stable and the other is least stable. Okay. First, staggered. Staggered. Eclipsed. Okay. This is most stable. Why? Because bonds are far apart. That means torsional strain is minimum. Minimum torsional strain minimum energy, okay, the energy will be minimum. And torsional angle will be maximum, okay. In the case of eclipsed, this is least stable. That means bones are closed. Okay. Torsional strain maximum. Maximum energy. Okay, maximum energy. That means torsional angle is minimum. Okay, minimum torsional angle. This much about the conformational isomerism.